Yeah, so I'm Durgesh. I'm a PhD student in UiT Tromsø, and I'm working with uh, anatomical motion mode imaging for left ventricle automatic measurement. And uh, I have been working on this project since beginning of my PhD, and some preliminary analysis and part of this presentation today has been presented before in previous VI sessions. But today I'll be presenting some updates, showing some interesting results, some animations, and some also discussing future directions and how anatomical motion modes can benefit in left ventricle automatic measurements, where the fully automatic V mode is has some limitations. So yeah, I'll be discussing all these things in detail in this presentation. So let's begin. A little bit about the domain knowledge first, for the people who haven't seen this kind of like echocardiography data. So basically, the echocardiography is like ultrasound images. So we have like an ultrasound scanner. So the scanner basically like emits sound waves which are reflected back from the organs that we want to scan, and these sound waves are shown recorded in a 2D screen, like the brightness of the sound, and this is called like B mode ultrasound. And whenever we are scanning the heart, then we call it like echocardiography, and cardio means heart and echo like with the ultrasound. A little bit about the anatomy of the human heart. So human heart has like 4 chambers, and it pumps the blood from lungs to the body and vice versa. And generally like it's very active muscle of the body organ, and it it is constantly pumping blood by uh, expanding and contracting. So the whenever this heart is expanding, the blood is filling in both chambers of the heart, and this is called a diastole phase. And whenever the heart is contracted, then blood is pushing out of the heart chambers, and this phase is called systole or pumping phase. So there are different ways that we can do this echocardiography of the human heart. So generally, like we fix a window. So the transducer has some sort of window. There are different windows, but for this project, like we use the data recorded in the parasternal window, so which looks like this, and sound waves are recorded along this left ventricle long axis. So the data is called Plaque's view data, and whenever like we record the uh, beating heart, like beat by beat image, then it looks like video this we call Plaque's view echocardiography video. And here I mean, in the data, like in the movie, like we have like generally concentrate on like single cycle for some sort of analysis. And in the single cycle, there are two specific frames called systole and end diastole frames. In the end systole and end diastole frames, the heart is like contracted the most or expanded the most. So these are like two frames where we would like to do some sort of image analysis, and perform some kind of like measurements for the heart, like different structures within the heart, and based on that we perform some cardiac diagnosis and determine the condition of the human heart. So the data that I work with is a private data set provided by GE Healthcare, and it's a very broad data set where the images are collected from different like hospital across the Europe and outside like Taiwan also. So that data is like labeled with different labelers and different phases also, like ES and ED, like both phases also. So let's little bit see about what this data is. So I will just describe the task of left ventricle measurement. So as I mentioned, we in the echocardiography video, we performed some kind of like measurement based analysis by looking each frame in the echocardiography video. And generally, the one task is called left ventricle measurement. So this is a left ventricle, this is left atrium, and this is the right ventricle, which is visible in this Plex view. And the goal is to like identify 4 or 6 coordinates in a straight line, and based on these coordinates we determine some lengths. We perform some length measurements which are called like IVS, intraventricular septum, left ventricle internal dimension, and left ventricle posterior wall. So we perform some length-based analysis, and based on these measurements from the obtained landmarks, uh, we perform further secondary diagnosis. So, as I mentioned, so in the whole echocardiography video, there are only 2 frames. So first, a human needs to identify the end systole and end diastole frames, which are called anchor frames, and then it they have to like assign 4 landmarks properly, and then perform the measurement. So generally, like whenever this task is performed manually, there is a high variability of intra-observer or inter-observer variability, and the task is like a bit difficult, and most of the time same user performs different measurements of the left ventricle. So for this task, it is imperative to do some sort of like automation using AI. So it gives us predictable measurements every time, and having to reduce intra and inter-observer reliability. Since this task is like a bit difficult manually, even like to perform manually by the human, then of course we have like very limited supervision for the AI also, and sometimes like the data and the supervision quality is also not good. So the data means like sometimes the echocardiography images are not properly recorded, or they are recorded from different types of scanners. So they have like different image quality, and if the annotations are performed by uh, inexperienced user, then sometimes we have uh, low quality of the supervision. Yes, so Generally, like people have tried to solve this problem by using the deep landmark detection models. So the idea is to train a deep learning feed-forward network and try to predict like a heat map corresponding to the landmark and do like heat map based regression or classification. So whenever we do this, a little bit about the heat map based regression, whenever we try to do regression of the heat maps with the ground truth annotations, so generally to improve the performance of the unit, label smoothing is done. So basically, it is a common knowledge in landmark detection based learning that whenever we perform some sort of label smoothing, basically placing a Gaussian based heat map uh, at the landmark location and then train the uh, neural network based on the Gaussian heat maps, then it improves the performance. And it also like leads to better generalizability of the unseen data and uh, gives like better landmarks. But the issue with the like labels smoothing with the heat map based regression approaches are that uh, oftentimes that neural networks don't predict like perfect heat maps and deriving the exact landmark location becomes difficult from the imperfect heat maps. So people have tried to do landmark detection using classification based approach. So in the classification based heat map regression, the idea is to divide the heat map into a grid where each grid provides a likelihood score. I mean, the neural network provides a likelihood score if the landmark is present or absent in this grid. So based on the post-processing or of the thresholding scheme, we can determine if the landmark is available at this particular location or not. So we can pinpoint the location of the landmarks using classification based approach, and some recent works like argue in favor of the classification based approach, and it kind of like works for facial landmark detection and pose estimation and stuff. But the problem with the classification based heat map approaches are I mean, the location of the landmark highly depends on what is the granularity or resolution of the grid that we define to train the neural network on. And sometimes if we have like very low resolution images or like bad quality images, identifying a particular location and finding the exact landmark is difficult. So to summarize, the regression-based approaches suffer from the label smoothing problem, and classification-based approaches depend on the resolution of the input grid to perform the optimal location of the landmark. So I will now discuss approach in this slide, and in couple of slides later, I will highlight like why we need to exactly determine the landmarks for left ventricle measurements, because exact location of the landmark becomes important when we are doing measurement-based analysis for left ventricle structures. So this work is a bit old, but it gives the basic idea of like how to train a landmark based detector for identifying the four coordinates, four or six like coordinates for the left ventricle. So they train a unit based model by placing Gaussian heat maps, and these Gaussian heat maps are rotated Gaussian heat maps, which are created perpendicular to the scan line at which the annotations are provided. Upon the Gilbert et al., they perform the heat map based regression, and they also extract the coordinates using a layer called discrete spatial numerical transform in a differentiable fashion, and they also like extract coordinates. So this is how the landmarks predicted by the trained neural network. So in the red, these are the predicted landmarks from the neural network, and the green one is the ground truth. So basically, in this for training the neural network, the unit Gilbert et al., they use a multi-component loss function, and to correct the location of the landmark, this multi-component loss function has loss based on the heat map regression, and they also perform include the losses corresponding to the L2 distances between the coordinates, and also they measure the distance measure and form a loss based on that, and also the angle. So let's discuss now why they perform this multi-component loss. Suppose like we have a really nice looking image, and a neural network predict the four landmarks in a straight line based on the heat maps shown here, the symbolic heat maps. Then we can correctly measure the left ventricle structure. Why I am saying what is the criteria of correctly measuring the left ventricle structure is clinicians prefer to perform the measurements in the same level in a linear fashion on a scan line basically, and this orientation of this scan line should be perpendicular to the structure that we are trying to measure. And if we don't perform measurement in this fashion, then for example, this is a typical prediction from the neural network, and the fully automatic neural network thinks the landmark should be like this. And if we don't perform measurements at the same level perpendicular to the structure which we are trying to measure, then in this case we are overestimating, and here we are underestimating the actual measurement. And since the IVS wall thickness and LBPW thickness are very, very small, so even achieving a small error also leads a misdiagnosis of the different heart conditions, and it also leads to further potential misdiagnosis of general health condition. So in most of the cases, since the predicted landmarks from the fully automatic model, they are not perfect because of the label smoothing problem that we discussed before. So we sort of get like crooked landmarks. So individual landmarks can be shifted along this boundary of the structure that we are trying to measure, and for some structures, like we have this overestimation, and for some structures, like what we're trying to measure from the neural network, we have like underestimation. So I showed like overestimation and underestimation cases like here. So for example, here it's like underestimation. Had we were measuring like here, then and this measurement would be like little bit longer. And this is the case for the overestimation. So general landmark detectors are good. I mean, if we have like some approximate idea of the landmarks in some different domains, then sometime it is good. But for left ventricle measurements, even though like these are plausible landmarks, but they make like less clinical relevance as they are not correctly positioned, because these based on these landmarks we might derive incorrect measurements due to imperfection of the landmark placement by the neural network. And also like so these the previous B mode brightness mode based approaches are also trained with uh, annotation levels at this basal level. So the basal level is called like level at the mitral valve tip. So this is a mitral valve tip, and they don't offer any flexibility to perform measurements like some other level other than the basal level. So, but there is a recent study like in a medical field where clinicians also show that if we perform measurements at the mid-ventricular level, then it better predicts the further diagnosis of the heart. But to like train a neural network model, we need to like obtain the data for mid-ventricular level, and we can just repeat the training process. But a neural network model trained with single like level, fully automatic model often does not have like any flexibility to perform measurements at different levels. So generally 2 levels are accepted for doing left ventricles like measurements, which are shown here, basal level and mid ventricular level. So now like I just show an idea called anatomical motion mode based left ventricle automatic measurement. So what is anatomical motion mode is basically a computationally derived some sort of like time based image where given a scan line, we sort of like trace the left ventricle structures along the scan line. And because in a single cycle video we have like multiple frames, so we like utilize the time component and get an image like this, where we change the image space from B mode to like motion mode, because this image depends on motion of the different structures of the heart. And we can even perform the left ventricle measurement in the anatomical motion mode. The good thing about performing left ventricle measurement in AMM mode is basically since we are, it's like one-dimension image across the time domain, and whatever measurements like we are performing here by identifying 4 landmarks, they are along the scan line from which this image has been obtained. So clinicians like generally take the help from AMM images also while performing measurements in the B mode. But the current medical guidelines, they recommend to perform the measurements in the B mode, but as I mentioned, the echocardiography images are of different quality, and if the structures are not clearly visible in the B mode, then sometimes like plotting this AMM-based image like helps to see how the motion of the different structure walls are happening, and then it is like I mean a little bit further help while identifying the landmarks by looking two modes side by side. But the guidelines like say that we have to perform the measurements in the B mode only. So this work is like very like intuitive, since like the problem from the fully automatic approaches that we discussed is like overestimation or underestimation, because the predicted landmarks are not perfect. Like precise landmark placement does not happen because of the imperfect heat maps, and for a clinical perspective, we need like landmarks in on a single line, which we call like a scan line. And so what we did, we just like computationally derived the scan line from the training data, like because we have like 4 coordinates are provided, and we derived a scan line, and around the anchor frame, like we computationally created a simple AMM image by tracing left ventricle using our interpolation function T. And based on this AMM image, we train the identical landmark detector and try to predict the landmarks in one dimension only across the y-axis, because since we are restricting the landmark prediction by changing the image space, then our problem is now more constrained, and it becomes more easier, because now I mean, we mitigate the imprecise placement of the landmarks, because the motion in like the degree of freedom is along the scan line itself, and it makes the like it solves the problem of the crooked landmarks. So we just did we are proposing this algorithm, which is very easy to compute, and it does not require any fancy computation, just interpolation function along the derived scan line, and we just train an identical landmark with the same loss, and other training settings are exactly same. And whenever we predict the landmarks, as we see in just a second, yeah, in this figure. So as we see, like here in this case, the B mode is sort of giving us imprecise landmark placement, and for the same image, if we constrain the landmark prediction using AMMs, then we get the landmarks along the given scan line. But the issue with this approach is For the training time, we derived the scan line from the coordinates which are already provided. But for at the inference time, like a user need to provide a scan line. So in this way, this method is semi-automatic. Uh, it's not fully automatic because user need to uh, provide the input where they want to measure the landmarks, and the model performs the LV measurements by placing 4 landmarks across the line. But having a semi-automatic model is not bad, because I would say that this left ventricle measurement problem is kind of like subjective, and different users have like different ideas where the measurement should be performed. And generally for the same image, as I mentioned, there is like inter-observer variability. Two different users like will select two different levels, and they sort of like perform. I mean, the idea of like where the mitral valve is may be different, and it also depends from like user experience. I mean, we need to have like some sort of like flexibility where the user thinks that the measurement should be performed, and having a human in the loop also benefits that we can perform measurements at the basal level as well as like mid-ventricular level, which was the study in 2019 study that I was discussing in the previous slides. And we can perform measurements in the basal mode and the basal level and mid-ventricular level without having to train the neural network model with the supervisions at mid-ventricular level. So because user can just like provide an input, the scan line should be at mid-ventricular level, and this model will provide the 4 landmarks along the scan input scan line. So we did we computed some numbers, and so in the landmark detection problems, so mean absolute error and mean absolute percentage error and the coordinate errors are like very common evaluation metrics. And as I mentioned, if we keep all the training protocols same and just do this B mode to AMM algorithm, then we sort of like improve on an average over the test data, and without doing any extra complicated pre-processing or design, we sort of improve the baseline. We also performed some bland Altman plots. So in the bland Altman plot, based on the mean absolute error, I show the B mode error and the difference of the MM. So here in this part, B mode error is high for 3 different structures, like 54% of the cases, and we see that we are able to reduce the mean absolute error by proposing the AMM-based landmark detection. Similarly, like I also do some success detection rate for different levels of the threshold. So in success detection rate, basically we decide different levels of the threshold, and if the network make error less than that particular threshold, we call it as a success case, and other is like failure. So for left ventricle measurements, like generally people do the SDR analysis for 0 to 2 millimeters, and it can be seen that by this AMM-based approach achieves a higher success detection rate for when compared to the B mode baseline. So now I would just previous analysis were done where when we know that the scan line provided at the training and the scan line provided at the test are identical. So that's, I mean, that is the only way like to compare the B mode and the AMMs. But if we want to like see how the model is robust for different perturbations of the scan line or even different frames, then I am just able to show the these animations where here in this animation it is shown that model is the MM model is trained only on the one frame, and if we just try to have some fixed scan line but change the different frames, then how the B mode and the AMM model assigns the landmark. Since here the scan line is fixed, then the AMM model always try to place the landmarks on the scan line, so there is less jitter because we are constraining the landmark prediction. So this animation is good, but like sometimes here I just provide a general rotation of the scan line and try to see how the AMM model detect like landmarks. I mean, we don't have the ground truth to compare it, so I just do qualitative visualization. But it seems that if the rotation perturbations are like not much, and if they are like in vicinity of the gold standard scan line, then the model sort of like manages reasonably. Here the scan line is like sort of like getting shifted, and based on different like positions of the scan line, we sort of get like different AMM images, and we see that if we shift the scan line not too much from the correct position, then the neural network manages to assign like 4 coordinates across the boundaries of the left ventricle. So, I mean, this model is kind of robust if we perform like small perturbations to the scan line locations. So it can be used to perform different measurements at the different levels without having any additional training. Here in this animation, I am like doing some uncertainty based analysis. So the idea is like if the rotation is too large, then I should get like high uncertainty for that particular point. And if the rotation is like small, then I should get like low uncertainty. But I must admit that these are some nice looking images. Sometimes like it's different structures in the left ventricle are like barely visible from the eye. So, I mean, this uncertainty based approach is kind of like, I mean, not approach, like uncertainty based analysis is kind of like, it doesn't give any fruitful result to filter out like incorrect orientations of the scan line. But to do this kind of uncertainty based study, I did some plots. So the previous work that I did is semi-automatic left ventricle automatic semi-automatic left ventricle measurement model using the same like architecture, and it's kind of like solves the overestimation and underestimation of the B mode approaches, because we do the landmark prediction on a constrained straight line. And now we are thinking to like make the model fully automatic, but keep all the properties, nice properties of the AMM images. since like assigning the landmarks are like a little bit easier. So so this work is in progress, that I'm currently doing some experiments, but I thought that I should share some updates, what I have been doing. So basically I am training again a simple feed forward network, pre-trained network on the ImageNet weights, and just assign some random locations of the scan line. And if the scan line is very near to the ground truth scan line, which is already provided in the data, I call it is, I call the resulting image as correct. Otherwise, I call the resulting image as wrong image, and I just train a binary classifier to see if the resulting generated when I feed the resulting generated image to the neural network and train it, then is the neural network sort of like able to identify if the given input, the AMM image is correct or not. And based on that, I can use this information to check if given a scan line, is it at correct location or not. So I do this kind of like training where I just sample some data for different perturbations of the scan line. So S is the shift axis and R is the rotate axis. So I think we have very less time, so I should finish this first. So, and I try to like form this kind of curriculum where I just first give like easy examples. I mean, if the scan line is like so far, then try to say that this is a wrong AMM image, generated image, and if the perturbation is very near to the actual ground truth scan line, then I say it is the correct AMM image, and I just like try to see how the neural network trains. And this plot is showing some sort of like density based analysis where for at the inference time for each combination of shift and rotate in this region, I sort of like plot the confidence. I do plot the confidence of this model. So this is how the model predicts. So based on this density-based analysis, the model thinks these are the probable locations where the model has like high confidence for the AMM image to be correct AMM image. What the model has seen as part of the positive class while during the training. And if we see this figure, I mean, there could be like there are multiple candidate locations where the model, I mean, here I am taking the left edge of the cone as the baseline and try to shift using the shift amount, and this rotate shows the anti-clockwise rotation. And we see that there are multiple candidate locations for a particular value of the shift. And so this is like how the density plot is shown. So there are multiple correct answers, but the model tries to like find some sort of like region, like the shift based region is like some sort of like correct because it is detecting at the mitral valve tip. And now we need to like correct the rotations also, because it thinks that at around like 30 pixels, like it should be like shifted from 30 pixels from here, that where the scan line should be placed for doing left ventricle measurements. And for the rotation, I'm testing from -20 to 20. So there are more than one values where the confidence of the neural network is particularly high. So that's why like it's not perfect, or like trying to find out the correct optimum point where the line should be placed. And this density based analysis we can like do smartly. We can do some like sampling algorithms to sample from this density. So we don't need to like test for each possible combination. We can just do some sort of sampling. So another idea that I think that since AMM based like approach, the previous AMM model is like semi-automatic. It needs like the position of the line, and this AMM this AMM sort of like gives the position of the line. So why not like combine the two models? So if I get the position of the line and I try to like do perturbations near in this region, I sort of like get the contour of the left ventricle. So I mean, these images are not like same images because I did these three kind of experiments. And based on whenever we know the contour of the left ventricle, because this AMM model is like robust in near perturbations of the original scan line, then we sort of like determine the left ventricle long axis and try to correct the prediction of this network. And we do this like in circular fashion and try to like correct the rotations. And I mean, this model gives the feedback from this model, and this model can get the feedback from the right model. So in this way, like I'm doing some experiments, and I'm trying to like correct the rotation and try to make this approach fully automatic by training the two approaches and proposing some algorithm to automatically perform clinically relevant LV landmark measurements. So in summary, like we discussed, this left ventricle automatic measurement task is difficult because of absence of high quality training data and the supervision. And we saw that if we just use fully automatic landmark detectors, then they often give overestimation or underestimation of left ventricle measurements. And we sort of like derived this semi-automatic approach, which creates AMM images and try to mitigate the overestimation or underestimation problem. And then also like in point number 4, I tried to sort of like comparing AMM images. I try to get some intelligent estimate where the scan line should be. So the same like comparing AMM images, like I try to find where the scan line should be by training a neural network with the same supervision, like the 4 landmarks that I have we discussed, and try to like take these two models and combine the predictions of the two models to correct the predictions of both model by estimating the left ventricle geometry, like the contour, and fix the location and rotation problem. So I'm still doing some experiment regarding this, but it seems to me like I mean, that's why I don't have like any numbers to show, and I want to like further analyze how much of the can I further like improve the quality of predictions and do more clinically relevant predictions for left ventricle measurements. So yeah, I think that's all. This is like some updates that I wanted to discuss for this seminar.